Hello, welcome again, Mr. Juma here to lesson number 6. So in this lesson, we are going to discuss application of the equilibrium rules, those factors that affect the equilibrium, which we had: the concentration, temperature, pressure, and even catalyst. How are they applied in industries, in the production of goods and goods? In last lesson 5, so we discussed those factors, how they affect the position of the equilibrium. Now, the application. Those rules are applied for two main reasons. One is to have the highest possible yields, that is maximizing the product, and then the other reason is to have minimum leftovers of the reactants. As I gave an example last lesson of ammonia, usually about only 10 to 15% of nitrogen and hydrogen is converted to ammonia. So the ammonia produced, you find in relation to the amount of nitrogen and hydrogen, a lot of nitrogen and hydrogen are left unreacted. So to make sure that most of the nitrogen and hydrogen are reacted to produce as much ammonia as possible, so it will be good to look at the factors that will give us the best yield of ammonia. And so we're going to discuss those rules. So there's the rule on temperature, and let me just project these ones on your screen so that they'll be much more clear than on the whiteboard. Okay, the rule on temperature. So if the forward reaction is endothermic, raising the temperature favors it. That means more products are going to be formed. So for endothermic reaction, use higher temperature, you will have more products formed. Now, if the reaction is exothermic, if the forward reaction is exothermic, decreasing the temperature favors formation of more products, because in the industry, your aim is to produce a particular type of goods, so you want to have the factors that will give you the highest yield. So if the reaction taking place is endothermic, use higher temperatures, but if the reaction is exothermic, you use lower temperatures. Rule number 2 on concentration. If the concentration of the reactants, that is on the left hand side, is increased, then some of it has to be converted to products, that is on the right hand side, so as to maintain the equilibrium. That means the equilibrium will shift to the right. So one way of increasing product formation is to increase the concentration of the reactants, so that once you increase the reactants, the concentration of the reactants, the equilibrium tries to cancel that effect by making sure they are used up, so as to lower their concentration. In the process, more products are formed. And if the concentration of the reactant on the left hand side is decreased, then products will be formed back in the reactants. But I don't think you can have an industry where you are manufacturing commodities and then you are converting back to the raw material. So here the best will be either increase the concentration of the reactants, or the best way also to effect concentration is to remove the products formed. So by continuously fetching the products formed, you are constantly lowering the concentration of the product, and the effect is that the equilibrium will keep shifting forward, trying to re-establish itself again. So by so doing, more and more of the reactants are used up. So this minimizes leftover, at the same time maximizing the yields. Then the rule on pressure, that will be rule number 3. Increasing the pressure favors the side of the equilibrium with the least number of moles or volume ratio, as we discussed in the last lesson, that is for gaseous molecule. So here you have to consider the equation. Now, if the reactant side has higher mole ratio than the product side, then using higher pressure will make sure that the forward reaction is favored, so you'll have more yields. But if the reactant side has smaller mole ratio, then use lower pressure, because decreasing pressure will favor the side with the higher mole ratio, so that Now the product side, since the product side has higher mole ratio, it will be favored by lower pressure. In the result, or the end result, is that you will obtain more products, because the aim here is to have as much yield as possible. And then on the catalyst, the rule on the catalyst, as we have stated earlier on, the catalyst does not affect the position of the equilibrium. However, when used, the equilibrium is established faster. Now, this has two benefits. One is that it makes reactions with higher activation energies to take place at lower temperatures. Hence, you will save a lot of heat energy. So if you are using, for example, electricity for heating, so the bill for electricity will be much lower, because you are using just small amount of electricity to do the heating. And this also saves time by establishing the equilibrium faster. So they say time is money. So if you can have your products produced within shorter time, then that also translates that, it means that you can produce more products. Therefore, if you sell more, that maximizes your profit. Just to note that once an equilibrium has been established, you can always introduce a stress into the system by removing some of the products. So the system will produce more by trying to establish a new equilibrium. So this is usually one of the most effective way of effecting particularly concentration, so that you have very little reactants being left as leftovers. So by so doing, you have a lot of products produced, yet most of the reactants will be used up. So the system itself will always try to establish a new equilibrium. So you destabilize the equilibrium, the system reestablishes it again, remove the products, you have destabilized the equilibrium, then it produces more products to establish a new equilibrium. So you keep doing like that, and at the end of the day, you have a lot of products formed and removed from the system, and the system trying to produce more products to replace those that you have removed. And that is how industrially it is applied. Let's just look at some practical examples which industries particularly apply some of these rules. So an example of an industry where these rules are applied is in the Haber process, in the manufacture of ammonia. As you can see the equation there. So applying the rules, so we have the rules on pressure, we have temperature, and also catalyst. So here in this case, if we use high pressure, it will favor the side with the smaller mole ratio. That means on the reactant side, because you can see the product side, we have 1 mole ratio of nitrogen and hydrogen, as I had explained in the previous lesson. And then on the product side, you have 2 mole ratio, totaling up 4:2. Let me just illustrate that on the whiteboard. So this is the equation for production of ammonia. So the mole ratio, so we have the factors like pressure. So let's start with the factor or rule 1. We have pressure. So in the manufacture of ammonia, the pressure applied between 250 atmospheres to 500. So a pressure of 250 atmospheres to 500. So this will be the optimum. The best pressure applied, I'm going to explain later on something concerning these same rules in manufacture of ammonia. So we say that for pressure, we consider the mole ratio. So this is 1:3. It's supposed to be 2:2. So the total mole ratio of reactants is to products. So we have 1 and 3. That gives us 4 and gives us 2. So in this case, high pressure favors the side with small mole ratio. So it will favor the product side. So that means high pressure. So 250 pressure is a high pressure. So high pressure will favor production of more ammonia. And then we have another one of temperature. Now, in the manufacture of ammonia, a temperature of 450 degrees Celsius, or 400 to 500 within that range, and with the best condition for temperature is used. Now look at this, the reaction here is exothermic, yet we are using such high temperature. Now, the reason why this temperature is used is because of the nitrogen-nitrogen triple bond. This triple covalent bond is very strong. A lot of heat energy is required to break this bond. So for the nitrogen to react, high temperatures are required for it to react. But once this reaction starts, a lot of heat is generated. Therefore, cooling is required to maintain it to lower temperature. Otherwise, if cooling is not applied, so if lowering of the temperature is not applied, then the production will be ineffective, because too high temperatures will favor backward reaction. At very high temperatures, the ammonium form will be converted back to nitrogen and hydrogen. So as much as this is high, but more heat energy is produced. So that which is more that is produced is where now the law will be followed. But initially, if you are to say now, because the reaction is exothermic, if you start with very low temperature, this reaction will not take place because of the nitrogen-nitrogen triple bond. So the law on temperature is not strictly followed, including even pressure. So we have said that even for pressure, the higher pressure, and here we have given a range of up to 500 atmospheres. And then we are saying that this will be the best temperature pressure application. Now, why will we not take this, since high pressure leads to more yield of ammonia? Now, maintaining this high pressure is very costly. So in the long run, you might find that the process becomes very expensive. Very high pressure is expensive to maintain, to lead to bursting of the tanks, that's the compressors. So those replacements from time to time, it will be very, very costly. So the best the adopted pressure will be of 250, and then we had on catalyst. So this equilibrium can be made faster if we use finely divided ion. Finely divided ion catalyst is used to speed up the reaction. And then finally on concentration, ammonia produced, so here you keep removing ammonia formed. So once you keep removing ammonia formed, then that will lead to production of more ammonia so as to establish a new equilibrium. So let's consider another example. So our next example, contact process, manufacture of sulfuric acid. So this is a very crucial question. There are many questions in the entire contact process, but usually this is the most crucial question of contact process. Manufacture of sulfur 6 oxide. So in this case, for this reaction to take place, here there are a number of factors that have to be considered. Pressure, temperature, catalyst. So let's see how pressure is considered here. So remember, we have said high pressure favor the side with small mole ratio. So let's consider the mole ratios. This is 2 is to 1 is to 2. So that is total of reactant is to product. So we have 2 in 1, that is 3 is to 2. So here we find that again, just like in in the first example, the products have a small mole ratio compared to the reactant. That means high pressure here will favor formation of sulfur 6 oxide, and here a pressure of 2 to 3 atmospheres is applied. So this will be the best pressure to have more yield of sulfur 6 oxide. Then again a temperature similar to that, 400 to 500 degrees Celsius. So you can take an average of 450 degrees Celsius. And then also a catalyst is used so that this equilibrium is established faster, of the reaction to occur faster. The catalyst used here is vanadium 5 oxide. Vanadium 5 oxide. So this substance is used as a catalyst to speed up the reaction. Do it now. Then you see those rules which we had 4, now already 3 applied. High pressure, so our pressure will be considered. Temperature. Now plus heat. If you see plus heat, it means heat is given out, it is generated. So this is an exothermic reaction. However, sulfur 4 oxide does not really react with oxygen. A lot of heat energy is required to make sulfur 4 oxide react with oxygen. That is why this high temperature is used. But once this reaction takes place, a lot of heat is generated. Therefore, cooling will be necessary so that we favor formation of more sulfur 4 oxide. So from there, the law on cooling on temperature follows, because the forward reaction is exothermic. So keeping temperatures moderately lower, that is not to go above 500. So if it reaches 500, you have to make sure you keep lowering that temperature to as low as 400. So it should range between 400 to 500, an average of 450. Then as a catalyst, we have seen. Then you can also effect the rule on concentration. So by constantly removing sulfur 6 oxide formed, in this case, the sulfur 6 oxide is dissolved in concentrated sulfuric 6 acid to form oleum. Which is then diluted in water to form sulfuric 6 acid. So the oleum formed is then diluted in water, then it forms sulfuric 6 acid. So this way, removing sulfur 6 oxide will reduce the concentration, so more of it is formed. Then now sulfur 6 oxide is not dissolved directly in water. The reaction is highly exothermic to produce the vapor of the acid, so it will be difficult to collect those droplets of the vapor of the acid. So the best way is usually to dissolve sulfur 6 oxide formed in concentrated sulfuric 6 acid to form oleum, then you dilute it. That will give you sulfuric acid. And those are the 2 good examples that we can consider under industrial application of those rules. And that will mark the end of our lesson number 6. So the lesson number 7 will be our last one to consider just small portion of this topic remaining.